Hello everyone, welcome to the course on medical biomaterials. Now we are going to talk about properties just as biodegradation or bioresorption. We are going to see what is the difference between this degradation and resorption in the human body and how it is going to help, because in many systems we do not want the material to stay inside the body, we want the material to leave the body after it has done its function. So, the properties of biodegradation or bioresorption are incorporated into the material. Okay. So, when do you need biodegradable polymers in medical biotechnology? For example, if you look at wound management, okay, in the wound management area, sutures, we want the suture to completely disappear after the wound has healed, or staples, clips, adhesives, surgical meshes, all these once it has done its job, for example the wound has healed, there is no infection and tissue has grown, we want this material to completely degrade. We do not want a material which does not degrade and remain in the body forever and ever. Orthopedic devices, they use quite a lot of pins in orthopedic implants to keep the stainless steel or titanium in its position. We want the pins to degrade once the implant got in line with the bone. Rods, a lot of rods are used, screws are used, so we want all these to degrade after it is done its job. Tacks, ligaments in orthopedic area. If you look at dental area, guided tissue regeneration membrane, void filling. So, after a tooth extraction we are filling the void and we want slowly the material to grow on its own. So, we want degradation. Cardiovascular application, stents, currently metal stents and drug eluting stents are used and they are quite widely used. Ideally we would like the stent to degrade after a few months so that there is no titanium or stainless steel inside. If the stents do not degrade and we have placed a stent, the doctor is not able to place another stent inside the body. That is one problem. Another problem could be sometimes stents start migrating, that means they move from one place to another and they may block some artery. So, ideally we want the stents to completely degrade after a few months and so on. Then intestinal applications, anastomosis rings, drug delivery system, you are delivering drug to your targeted site and then once the drug has been delivered, we want the polymeric material to completely degrade and disappear. Tissue engineering application, we use scaffolds for the tissue to grow. Once the tissue has grown and then it has occupied the void, then the scaffold material should completely disappear, we do not want the scaffold to remain. So, in all these areas we would like the material to completely degrade and come out of the system or get completely resorbed. Okay, now what is the difference between biodegradation and bioresorption? Okay, there are a lot of differences there. Biodegradation, so if you have a polymer, a large molecular weight polymer, when it degrades it becomes a macromolecule. So, a 60 kilodalton say ultra high molecular weight polyethylene for example may degrade into smaller molecular weight, maybe about 10,000 or 5,000 or 15,000, they are called macromolecules, okay. But they may stay inside the body and migrate, okay. So, it is degraded into smaller molecules, but it might not be completely eliminated, they may be in the circulation, but still it is biodegradation. So, from maybe about 60,000 like I said, it may come down to 10,000 or 5,000 of molecules of macromolecules of different molecular weights. For example, ultra high molecular weight polyethylene, this is used quite a lot in joint prosthesis. Suppose there is a joint replacement, they use metal and metal interaction is not very good because it rubs and it leads to release of fine metal. So, they use ultra high molecular weight polyethylene which acts sort of a lubricant. So, even that gets degraded into smaller molecular weight, that is called biodegradation. What is this bioresorption? So, the entire material gets degraded in vivo and it is eliminated from the body into very low molecular weight molecules. Okay. So, if there is a 20,000 molecular weight material, it gets resorbed into very small molecular weight material and it gets eliminated completely. For example, if we take polylactic acid is a FDA approved polymer and is used in quite a lot of implant, especially in drug delivery and so on. So, it gets completely bioresorbed and there is nothing left inside, it goes into even lactic acid and that gets eliminated. That is called bioresorption. So, sometimes metals are also classified as bioresorbable. Okay. So, if for example, rubbing of metal or corrosion leads to the elimination of the material, so it may slowly come out of the body, but this could be a much longer when compared to polylactic acid bioresorption, which is very fast. So, although metals we cannot call it bioresorbable, but it is still called because corrosion may lead to total elimination of the material, or even rubbing of material metals can lead to final powder which may be get eliminated, but it could be much longer duration. Then we have bioerosion. Materials are first degraded on the surface and then it is resorbed in vivo, okay, that is called bioerosion. And then bioabsorption. So, materials could dissolve in the body without modification of their molecular weight, unlike the bioresorption. Please understand, in bioresorption the material degrade into smaller molecular weight and then gets eliminated, whereas in bioabsorption the material may be resorbed without actually degrading into smaller molecular weight material. Okay. So, these are the different types of changes that could happen to materials that are placed in the body, and as I said it is very important in many situations to have biodegraded or bioresorbed polymeric material as a implant. So, the resorption of a material consists of several factors. How much water gets absorbed, because water may get involved in the hydrolysis reaction. So, after it starts getting slowly degraded, there could be reduction in mechanical properties, that means the tensile strength may change, modulus may change, reduction of molecular mass, that means the material may be lost in the weight, complete loss of weight. So, the material could be completely losing its weight, then it may be becoming smaller and smaller and then finally disappearing. So, that is what it means, resorption. For example, I just want to show you a few pictures. Look at this. This is a surgery, orthopedic surgery. What they do is because there could be a lot of infection that could be happening after placing a metal orthopedic implant. So, what they do is they use a polymethyl methacrylate beads which are impregnated with an antibiotic like meropenem, for example. So, they keep these beads inside and close it after doing the implant. So, the polymer slowly releases the drug meropenem, thereby it prevents the infection and biofilm formation. But the problem with the PMMA is it does not get degraded, so it has to be removed later on. So, they will do a small surgery to remove that. So, this is a bit painful because it is non-biodegradable or non-bioresorbable. So, ideally one would like to have a nice polymer which is able to take in lot of drug, encapsulate a lot of drug, it releases the drug, say for example within 6 to 8 weeks, and then it also starts getting bioresorbed or biodegraded. So, the doctor does not have to perform a second surgery. Okay. So, ideally this picture is a courtesy from CMC Vellore in Tamil Nadu. Now, look at this, and this is a polyurethane urethral stent. Okay. So, this is called a urethral stent. It is placed inside the ureter region which connects both the kidney and the ureter. So, the urine flows nicely down. Sometimes this ureter can get blocked because of infection, or if there is stones in the urine, sonication is performed to break the stones. So, you need a nice opening so that the small broken powder stones can flow down. So, they place this particular material called a urethral stent. It is quite flexible, it is made up of polyurethane. So, after about 5 to 6 weeks and the doctor has to perform another surgery to remove this. Ideally, if we have a biodegradable material, so the doctor places the material stent inside, it performs its duty, and once it has performed its duty, it should degrade or bioresorbed completely. So this is another example of where I would like to have a biodegradable material like an urethral stent. This picture, this X-ray is a courtesy from Dr. Shroff of Sri Ramachandra Medical College in Chennai. Look at this, these are stainless steel bone plates. Okay, so after an orthopedic surgery, these bone plates are placed inside to connect the bones here using screws, as you can see, and pins here you see. So it is placed like this. So the bone starts healing, the bone starts growing. So ideally after a few months, if the bone plate completely resorbed, then it will be nice, then the person will not have a foreign material placed inside. But as you know, currently stainless steel and titanium plates are used which are not biodegradable, so they remain inside the body forever and ever. This is another place where we would like to have a biodegradable bone plate, but it could be after 3 to 6 months, whereas if you look at the urethral stent, you would like to have it about 6 to 8 weeks, whereas if you look at the PMMA loaded drug loaded PMMA, in this area I would like the material to degrade in with about 15 days. So you can see different types of time durations are required. Here we would like the material to degrade in about 15 days, here we would like to material to degrade after about 6 to 8 weeks, and here we would like to have the material degrading after about around 6 months. Okay. So if you have a biodegradable bone plate, okay, we will not require another surgery for removing the bone plate. Generally you cannot remove the bone plate because the bone nicely grows and as muscles grow, so absolutely not possible. We can also avoid stress shielding if the stainless steel material is not there, because there will be only one material, that is the bone, instead of having bone made up of hydroxyapatite and stainless steel. We can also have a controlled drug delivery. So if we have a polymeric material which may degrade over a period of time, which can be coated with drug gets released slowly, so it prevents the biofilm formation and infection. Okay, so the plate takes care of the mechanical strength initially, with time it degrades, so the plate is completely useless. In the meantime the bone starts growing, so the bone takes care of the mechanical strength requirements for the rest of the life of the patient. So ideally we would like to have the plate slowly degrading, and later on the bone takes care of the weight and other mechanical requirements. Okay. So these are few situations, I showed you examples where we would like to have this type of biodegradable bioresorbable material. Okay. These are courtesy, the photographs which I showed are courtesy from various places like CMC Vellore and Sri Ramachandra Medical College in Chennai. Okay, so what type of bonds in the polymer could degrade? Oxygen, nitrogen, sulfur. For example, look at this, this is an ester bond, we will say ester bond. Okay. So or this could be an amide bond, or this could be a thioester bond. So we have C double bond O, X could be oxygen, C double bond O, X could be nitrogen, C double bond O, X could be sulfur. So these bonds are easily hydrolyzable, that means water can react with that, maybe a little bit of acid, or if you have some enzymes, so it can generate acid like this. Okay. So if you have polymers which has backbones like this, or linkers which has like this type of setup, they can get hydrolyzed and they can degrade, okay, slowly over a period of time. Okay. So ester bond, amide bond, thioester bonds can degrade if the polymer in the backbone has these type of bonds. Okay. Or we can have these type of situations, okay, carbonate, these are slowly degradable, unlike the previous case where we have these are more faster degradable. whereas these will degrade much slowly. So we can have O and O, this is called carbonate, you have C double bond O, O and O, or we can have urethane, C double bond O, O, NH, or we can have urea, NH, NH and C double bond O. So these are also hydrolyzable, that means they can react with water, but they are slowly reacting, unlike the previous case. Or we can have other situations like imide, anhydride, again anhydride, imide, they can degrade much faster. So we have C double bond O connected by O, another C double bond O, or C double bond O connected by nitrogen, another C double bond O, or C double bond O connected by S, another C double bond O. So they can also hydrolyze to form acid and an ester like this. Okay, so imide is an example, anhydride is an example. Okay, so here we can have O on both sides, or nitrogen on both sides, S on both sides with a ketone C double bond O. So again this can give you a acid, okay, and another okay, hydrocarbon here, whereas this one we have C double bond O on both sides connected by an oxygen or a nitrogen or a sulfur. Okay, so these are various types of bond systems which are biodegradable. Okay, so if you are designing polymers with these type of backbones, then they are hydrolyzable, that means they can react with water to slowly. And as I mentioned, some of these bonds are degradable at a faster rate, some of these bonds are degradable at a slower rate. So if I am thinking about 2 weeks, 3 weeks degradation, or if I am thinking about 6 months, 9 months degradation, I can design polymers with these different backbones. Okay, so we have acetals, some examples. Okay, acetals, okay, oxygen on both sides like this, they can degrade. Hemiacetals, okay, so you have the ring system which are degradable. Ethers, okay, so like I showed you here, right, ethers connected like I showed you here, oxygen, these are okay, ethers which can degrade. Nitriles, okay, so the C triple bond N, they can degrade. Phosphonate, they can degrade. Polycyanoacrylate, so different types of bond systems that are degradable. So polymers, natural polymers or synthetic polymers. Natural polymers like fibrin, collagen, chitosan, gelatin, hyaluronic acid, cyclic glucons, okay, alpha cyclic glucons, beta cyclic glucons and so on. If you go to synthetic polymers, polylactic acid, PGA, that is polyglycolic acid or combination of lactic and glycolic, polycaprolactone, polyorthoesters, polydioxanone, polyanhydrides, polytrimethylene carbonates, polyphosphozenes. So a lot of synthetic polymers that can also degrade. Okay, a lot of natural polymers, a lot of synthetic polymers that can be degrading. So we can consider designing maybe drug delivery systems or scaffolds or bone plates using these polymers, and of course you need to match the other mechanical and physicochemical requirements initially for the material to hold. So you can also have enzymatic degradation apart from the normal hydrolysis type of degradation. Okay, so hydrolysis, like I said, anhydrides are very easily degradable, esters come next and so on. Okay, of course enzymatic, you can have lipases, we can have esterases, all these amidases if present in the in vivo system, they can also aid in the degradation. Some of the degradation is called homogeneous degradation, you can have heterogeneous degradation. Homogeneous means uniformly material, the backbone gets degraded. Heterogeneous means it gets degraded only at the specific locations where we have the sites, favorable bonds for it to degrade, and if the bond is not favorable for degradation, then it will not degrade. Okay. Bioresorption we can initiate by first solubilizing, like dextran, polyvinyl alcohol, polyethylene oxide. So the polymer solubilizes, okay, and then later on you can have an ionization, polyacrylic acid, polyvinyl acetate. For example, some of the polymer polylactic acid, you can have ionization. you can have enzymatic reaction, okay, polysaccharides, polyamides, you have amidases or you have esterases, or it could be simple hydrolysis like alipharic polyesters can get simple hydrolyzed and completely get bioresorbed. So, these are various situations. We can have solubilization which can lead to bioresorption, you can have solubilization followed by ionization, we can have enzymatic reaction after hydrolysis, okay, or simple hydrolysis without enzymes present. All these can lead to bioresorption. Okay, so we have a polymer and this bond is there, so it can get hydrolyzed, just plain hydrolysis, or we can have enzyme that is catalyzing the hydrolysis of this particular polymeric material. We can have two situations: surface erosion, that means the surface slowly gets eroded or degraded, or the bulk, the entire polymer gets degraded and the polymer sort of dissolves, or it is not dissolved, it is completely loses its molecular mass. So, okay, so two situations: surface erosion takes place, that means the sample is eroded from the surface, then mass loss is greater than the ingress of water into the bulk, whereas if the water ingress is much more and degradation take place, then that is called bulk degradation. So, example of surface erosion: polyorthoesters, polyanhydrides, that means the mass gets lost very fast when compared to water ingress into the polymer. Bulk degradation like PLA, PGA, PLGA, PCl. So, the ingress of water is much faster than the rate of degradation. So, water goes inside and the material starts degrading, okay, that is called the bulk degradation. So, we have surface degradation. So, in bulk degradation the degradation takes place throughout the material, whereas surface degradation takes place at the surface, because the water ingress is much slower than the mass loss, whereas in bulk ingress of water is much faster than rate of degradation. So, if you have a surface erosion situation may be like this material may be becoming thinner with time, whereas in bulk erosion material may be getting lost inside, you may start forming pores inside, material may be crumbling, material may be breaking into pieces. So, all these can happen in bulk erosion, whereas surface erosion material will be uniformly getting thinner. Bulk erosion material may break into pieces, material may form pores inside, material may break at various places getting chipped because of bulk erosion. So, situations depending upon the type of situations, even depending upon the thickness of the material, it could have surface erosion or bulk erosion. So, pictorially we can show it like that: surface only and the surface material gets degraded. So, it is very nice to have if you are talking about slow drug release, whereas bulk erosion, as the water starts going in and suddenly there could be degradation taking place at various places inside the material also. So, bulk erosion, when water diffuses rapidly into a polymer leading to hydrolysis. So, this is a function of rate of hydrolysis of the functional groups, rate of diffusion of water inside the matrix, dimensions of the matrix. All these play a very important role in deciding the material is bulk or surface degradation. Okay, so, what is the critical thickness for resorbable polymers above which it's bulk or surface? Okay. So, if for these polymers, if thickness is less than this, it will be a bulk degradation. So, what it means is water has to ingress. If the water can ingress inside, then you can have a very good bulk degradation. If the water cannot ingress into it, that means the degradation is faster, then it will be a surface degradation. Okay. So, if the material is very thin, then obviously you are going to have a surface degradation. If the material obviously you are going to have a bulk degradation. If the material is very thick, water is not able to ingress inside, then you are going to have a surface degradation, and this dimension tells you whether it is going to be a surface degradation or bulk degradation. Okay. You can also have autocatalysis, because for example, if you take polylactic acid, when it degrades, it releases lactic acid, which is acidic and which may enhance the degradation further and further. For example, if you look at this particular picture, the rate of degradation versus time, initially the degradation is slow. So, maybe acids are produced or maybe some functional groups are produced during degradation, which enhances the degradation very fast. So, the degradation can suddenly shoot up like this. This is called autocatalysis. So, oligomeric hydrolysis products like carboxylic acid or other acids which may aid the degradation much faster, and this material is retained inside, they are not thrown out. So, it gets retained inside. So, it causes localized decrease in pH, that means material becomes acidic pH at different places, which can accelerate the rate of degradation. So, you may form hollow structures within the polymer, okay, because of these acids. Then this leads to rapid deterioration of the mechanical properties and sudden loss of structural integrity, like PLGA or PLA. Autocatalysis takes place because the acids that are produced in various places can enhance the degradation further and further. So, there could, these are sites where degradation are going to be much faster, that is called autocatalysis based degradation. Okay. Now, we can have different types of degradation. If you look at type 1A, so we have polymers, okay, they are connected by certain cross linkers. Okay. So, the polymer is stable, it is not soluble in water. The cross linkers could be covalently or ionically cross linked monomers. So, what happens after digestion of these linkages, okay, suppose these linkages degrade, then the fragments which are formed could be water soluble. Okay. So, if I have, say for example, collagen or gelatin which are cross linked, collagen and gelatin may be water soluble, but the linkages prevents them from degrading or water solubilizing. So, once the linkages disappear, then the remaining portions could be soluble. Okay. So, that is called a type 1 degradation. If you have type 1B, the digestion of the polymer backbone, okay, some portions could be degrading, that means they have relatively low molecular weight because of either chemical or enzymatic cleavage. Then the resulting fragments are water soluble and have a lower molecular weight. So, some portions of the backbone could be degrading because of presence of low molecular weight. Once they disappear because of degradation through enzymatic or chemical, the resulting fragments are water soluble because they have lower molecular weight, that is type 1B. Type 2, initially water insoluble, they may have some pendant groups which may get ionized or hydrolysis degraded. Once these pendant groups degrade because of hydrolysis, then the remaining polymer could be water soluble, that is type 2. Type 3, we have additional cleavage in the backbone. So, the backbone some portions can get degraded. So, you can have combinations of type 1A with type 3. So, initial cleavage of the cross linkers and then remaining backbone could be degrading later actually. For example, aliphatic polyesters, polyamides, polycyanoacrylates, polyanhydrates, polyacetals, polyorthoesters. So, they have cross linkers which may initially get cleaved, then the remaining polymer could be degrading in that. Okay. So, we can have combination. So, these are various situations by which we can create biodegradable polymers which may degrade with different mechanisms at different time periods. So, we have a lot of flexibility in designing polymeric systems with biodegradable properties. So, when we talk about hydrolytic degradation, so water is reacting with some functional groups. Okay. So, we can have acids catalyzing these, bases catalyzing these, even enzymes. So, as I mentioned before, so these are the situations where we can have enzymes also catalyzing or even bases may be catalyzing this type of reactions. So, a lot of these again, what as I showed again before, the catalysis could be taking place because of enzyme or acids or bases. Okay. I showed you before also. So, all these situations. Okay. So, we can have acids for water to react or bases or even enzymes which are catalyzing this reaction. Sometimes even ions could be catalyzing. You may wonder where are the ions in the body, but biological and cell cultured fluids contain a lot of ions, okay, H plus, OH minus, sodium plus, chlorine minus, okay, phosphate groups, potassiums, magnesiums, calcium, sulfate 2 minus and so on. For example, if you look at blood or extracellular fluid, you can see Cl minus, it contains a lot of Cl minus, carbonates, phosphates, sulfates, okay, hydrophosphates, sodium, magnesium, calcium, potassium. So, all you can see blood contains all these, as well as extracellular fluid contains all these. So, these could be catalyzing hydrolysis reactions, these could be breaking esters, amides, okay, and these could be breaking orthoesters, carbonates, okay. So, these could be catalyzing some of these reactions, okay, acid catalyzed, base catalyzed or metal catalyzed reactions, hydrolysis type of reaction. So, body contains so many metal ions both in the blood as well as in the extracellular fluid. So, they could be catalyzing many of the degradation process. So, even if you do not want degradation, sometimes you may be surprised the material is degrading because they are catalyzed by acids, bases and ions, okay. So, lot of these materials, nitriles, ethers, okay, phosphates, phosphonates, so all these are getting degraded because of presence of acidic ions or basic ions and so on actually, okay. So, quite a lot of situations where you can have sulfonamides, for example, produces acidic function, okay, polycyanoacrylate, okay, we have the cyano group here, okay, C triple bond N, C triple bond N, okay, and they are getting again hydrolyzed in the presence of base, okay. Sulfonamides, they are getting hydrolyzed in the presence of acidic or basic functional. Now, if you look at degradation of a polymer, okay, this is an example picture I am showing. PLA starting from 80 milligrams going down to 50 milligrams in 30 days, PLGA starting from 75 milligrams going down to 25 milligrams in 30 days. Gallic acid is more biodegradable than lactic acid, okay, as you can see in these two pictures, okay. So, by modifying the amount of glycolic acid in a polylactic system, I can modify the weight loss, okay, as you can see, and we can assume a first order type of degradation like this, weight loss is equal to weight loss at time 0 exponent minus kT, K value for PLA polylactic acid is 0.023, K value for PLGA is 0.068. So, I am having different by having different amounts of glycolic acid, I can achieve different degradation rates, which means I can have different K values here, and the degradation generally we can assume it as a first order, as you can see in this nice fit. This is the experimental data is the squares and diamonds, and the model fit is given by the straight line. This also shows you the scanning electron pictures of the degradation of both polylactic acid and polylactic glycolic acid system. Nice polymeric spheres here, as you can see, and with time it goes down, you can see nice degradation on the polymers of a certain diameter 270 nanometers becomes almost 100 nanometers in 30 days. PLGA starting from 325 nanometers coming down to 75 nanometers, okay, nice degradation profile you can see, and changes in the size of these polymers also, okay, you can see. So, if I am using this system for drug delivery, obviously if I have drug incorporated into this, as the polymers degrade losing its size, diameter, it may be liberating the drug, maybe antibiotic or anti-inflammatory drug. So, we can use the PLA or PLGA, both PLA and PLGA are FDA approved drugs, okay. So, we have very nice situation where we can have drug loaded polymers, and as you can see within 30 days we achieve almost 2 times reduction in the size with PLA and almost 4 4 times reduction in the size of PLGA. Okay. So, we will continue in the next class more on the biodegradation as well as bioresorption of polymeric material. Thank you very much for your time.